great pleasure to welcome Yini to tell us about Seifert fibered surgeries on hyperbolic knots.
Okay, thank you very much. So I guess it's my second time to be in Montreal, although virtually. Okay, so I'm going to talk about dense Seifert fibered surgeries. On hyperbolic fibered knots. Okay, so I guess first I'm going to talk about the dense surgery. So I guess you all know the definition of dense surgery. So I just quickly remind you. So if you have a knot in S3, and then you just remove a neighborhood of this knot and you glue back a solid torus such that the new meridian is P times mu plus Q times lambda. And we call this S3 P over Q. Okay. So this is the notation we're going to use. So now, Seifert hyperbolic dense surgery theorem says that if K is hyperbolic, then all but finitely many surgeries are hyperbolic. So from this theorem, you can get a definition. So if non-hyperbolic, if the surgery is non-hyperbolic, then we say it's exceptional. So a central question in dense surgery is to classify all exceptional surgeries. Okay, so, well, of course, this question is too big. So maybe it's not, well, maybe it's not possible to get a complete answer, but at least we hope to study some special cases. So by geometrization theorem, so it's due to Seifert and Perelman. If the P over Q surgery on K is non-hyperbolic, then there are three cases. Okay, so let's see what are the three cases. So the first case is this surgery has a finite the first surgery is reducible. And the second case is this surgery is so reducible means that IE contains an essential sphere, two sphere. Okay, second case is this surgery is toroidal. So IE contains an embedded essential torus. So other than these two cases, then the remaining cases, this surgery is Seifert fiber. Space. So from now on, I just use SFS. So Seifert fiber space. So I should say this contains the case pi 1 of S3P over QK. So this is finite. So when people talk about dense surgery, so in the literature, so usually when people say Seifert fiber surgery, they do not include a finite fundamental case. But here I want to include finite fundamental case as a subcase of Seifert fiber surgery. Okay, so these are the three cases of non-hyperbolic manifolds when you do surgery on K. Okay, now, so for these questions, so as I said, in general, it's impossible, probably impossible to classify all exceptional surgeries. But at least for some special cases, we do have some progress and we have some conjectures. So let me tell you about these conjectures. So first is the case reducible. So in this case, there is a conjecture. So surgeries, let's see, hyperbolic knots in S3 do not admit reducible surgeries. So this conjecture is known as the cabling conjecture. So this is one of the main open questions in dense surgery. So for the second case, well, the toroidal case is more complicated. So probably there's no good conjecture about toroidal surgery. So toroidal case is complicated. So when I say it's probably impossible to classify all exceptional dense surgeries, I mainly mean that it's probably impossible to classify all toroidal surgeries. Okay, now the last case. So in the last case, there is, in general, there is no good conjecture about Seifert fiber surgeries, but at least when pi 1 is finite, then there is a conjecture. So the conjecture is if the surgery has finite pi 1, then K belongs to two lists. So these two lists are due to Berge and also there is a sublist of Berge count. Okay, so a special case of this conjecture is also known as the Berge conjecture. So these are some main conjectures about exceptional surgeries. And I know some people in the audience have made a contribution to this conjecture. Okay, so now I guess I can state my main theorem. So the theorem I want to state is, so if you have knot in S3, it's a hyperbolic fibered knot. And the P over Q surgery on K is either reducible or atoroidal Seifert fiber. Okay, so it's either reducible or atoroidal Seifert fiber. Then there are two cases. The first case is if the monodromy of K is right-veering. If the monodromy of K is right-veering, then one can say that have a bound on P over Q is P over Q is between 0 and 4GK, where G is the genus, the Seifert genus of K. And if you also know that if K is also an aerospace knot, then 4GK cannot be attained. Okay, and the second part of the theorem is, so if the monodromy of K is neither left-veering nor right-veering. Then Q is equal to 1. And K is also an aerospace knot. Q is equal to 1, and this this surgery is irreducible. Okay, well, I guess here I forgot to mention another conjecture about Seifert fiber surgery. So let's see. Yeah, maybe I just add here. So right, so there is a conjecture about a Seifert fiber surgery, that is if this is Seifert fibered, then Q is 1. That is the surgery, any Seifert surgery coefficient has to be integral. So all these conjectures are stated for so maybe this is the case K hyperbolic. Okay, right. So if you look at these three conjectures, so then you can realize that the second part of the theorem of our theorem actually proved the first conjecture and the third conjecture in the case when K is fibered and the monodromy is neither left-veering nor right-veering. So remark, two settles conjectures 1 and 3 in this case. Okay, so you actually, well, of course, I guess that's just a small progress towards these two conjectures. But at least for fiber knot, now you can say something. So now in this theorem, I think I should explain some terminology in the theorem. So the first terminology I want to explain is L space. So this has something to do with Heegard floor homology, which I think you have seen before. So a rational homology sphere. But if you haven't seen it, well, I guess it doesn't matter. So a rational homology sphere Y is an L space if the rank of HF height Y is equal to the order of the first homology. Okay, so and when we say K is an L space knot, it means that a positive surgery on K has is an L space. So K is an L space knot if a positive surgery on K is L space. So that's about L space. So another concept I need to explain is the right-veering. So this is something probably less well known to people. So let's say we have a surface F is a compact oriented surface with boundary. Compact. The F is a compact surface oriented surface with boundary. So now let's say we have two essential arcs A and B on the surface. So let's two essential arcs AB in the surface with P is in both endpoint of A and endpoint of B. So I draw the local picture of the arc is like something like this. So this is A and maybe this is B. So two essential arcs in surface. Okay, now we say B is to the right. So right, I also equip F with a hyperbolic structure with geodesic boundary. So we can equip F with a hyperbolic structure with a geodesic boundary and let A bar, B bar be the geodesics homotopic to A, B in real boundary. Okay, so you can always straighten the arcs to get geodesics. Okay, so now we say B is to the right of A, maybe at P, if B bar is to the right of A bar in a small neighborhood of P, or just B bar is equal to A bar. So if B bar and A bar are the same, namely A and B are homotopic relative to boundary, then in this special case, we say B is to the right. So in general, it requires that in a small neighborhood of P, B bar is to the right of B bar. So in the picture, it's you just take a small neighborhood, and then you can find that B is to the right. So this is the definition of to the right. And now, so let phi from F to F be a diffeomorphism with phi restrict on boundary of F is identity on boundary. So let phi be such a diffeomorphism. Then we say phi is right-veering. If phi A is to the right of A for every essential arc. So a diffeomorphism whose restriction on the boundary is identity. And we say this is right-veering if phi A is to the right of A for every essential arc. So basically, it means that it just move every arc slightly to the right near the boundary. Okay, so this is the definition of right-veering. So I think this definition was introduced by Honda, Zetz, and Matisse. And they not only introduced this definition, but they also proved a very interesting theorem. So let's say, so this theorem also proved by them is that a contact structure on Y, on a three-manifold Y, is tight if and only if every, so let's call this contact structure C. So every open book supporting C has right-veering monodromy. So contact structure C on Y is tight if and only if every open book supporting C has a right-veering monodromy. So this so this tell you this concept of right-veering is quite meaningful in geometry. All right. So this explains. Well, of course, if a monodromy, if a map is right-veering, then its inverse is will be left-veering. So this explains the terminology in the main theorem. So if the monodromy is right-veering, then PQ has this bound. And if the monodromy is neither left-veering nor right-veering, then Q is 1, and the resulting manifold is never, the resulting manifold is never reducible.
So could you remind me what the relationship between right-veering and fractional Dane-twist coefficients?
Yes, yeah, that's a good question. So, yeah, right. So there is something called fractional Dane-twist coefficients. FDTC. So this is also defined for, so if you have phi in, let's say, automorphism of F and restrict to identity on the boundary, and then its FDTC of phi is a rational number. So at least for pseudo-anorthof map, so if phi is pseudo-anorthof, then right-veering, so phi is right-veering if and only if FDTC of phi is positive. Okay, so in general, I think it's a slight, so there is a, maybe there's a problem when the fractional Dane-twist is 0. Which I'm not quite sure, but at least for pseudo-anorthof monodromy, well, which is the case we're interested in here. So this is the same as fractional Dane-twist coefficient in positive. And that's an ingredient of our result. Okay, so so I guess now I can talk about some applications, so some corollaries of this result. Yeah, but before I talk about corollaries of this result, maybe I want to make a remark about the main theorem itself. So remark. So the main theorem is more or less known to experts on laminations. Well, but yeah, I don't think you can find an explicit statement in the literature. But it's somehow a result more or less known to experts on laminations. Well, but the point here is it becomes useful when combined with Hilbert floor.
So is that, when you say it's well known, do you mean part 2 is well known or part 1 as well?
I think both parts are, I mean, it's, you cannot find an explicit statement. I guess at least the reducible part is probably probably better known. But it's harder to really find an explicit statement in the literature. So you have to combine some sentences in one paper and some sentences in another paper together. So you cannot even find a explicit statement. There are only sentences outside of the main theorems and the properties. So you need to combine some sentences with other sentences and to get this result. So it's more or less known to experts. But the point is, it becomes useful when combined with Hilbert floor homology. So why is that? So the point is, in Hilbert floor homology, so a knot is fibered if and only if this knot is the topmost term of HFK has rank 1. So this is a result. So one direction. So let's say this direction is due to Oswas and Zabel, and this direction is due to Paolo-Gigini. So for the genus is equal to 1 case and mu the general case. So this tells you can use Hilbert floor homology to say whether a knot is fibered. So if you look at this theorem, one important assumption is that the knot is fibered. So this is something you can really use Hilbert floor homology to tell you. Okay, and another thing is in Hilbert floor homology, so there is a contact invariant. in Hegel floor homology, which can say things. So maybe I just say which is non-trivial, maybe which is trivial if the compact structure is over twisted. Okay, so so that's you can also use Hegel floor homology to say something about a tight compact structure. And then you use Honda, Kazet, and Matich's theorem. Then you can say something about right-veering. So in this theorem, there are two conditions which are not easy to check in general. One condition is this favored condition, and the other condition is the condition about right-veering. The first part is about right-veering, and the second part is about neither left-veering nor right-veering. So these conditions you can use. So in special cases, you can use Hegel floor homology to check these conditions. So although the theorem I stated was more or less known to the experts, but it becomes really useful if you combine it with Hegel. Okay, now I can say some applications of this theorem, which we use Hegel floor homology to prove. So this application is on characterizing slopes. So suppose K is a knot in S3, and we say a slope P over Q is characterizing for K. If for any knot L in the 3 sphere, the P over Q surgery on K is the same as P over Q surgery on L, implies K is equal to L. So here, this symbol means that they are homeomorphic as oriented manifolds. They are isomorphic as oriented manifolds. Okay, so for example, so I guess the first complete theorem on this is due to Kranheimer, Morufka, Osvas, Zabel. That is all slopes in R on the unknot. So all slopes are characterizing for the unknot. So they proved this general statement, but some special cases of this theorem were already proved by other results. For example, in the cyclic surgery theorem and in Gordon-Lucas theorem on knot complement, and in Gabbay's theorem of property R. Okay, and maybe I just write here. So Oswald and Zabel prove that same true for trifold, for the trifold and the figure 8. So Oswald and Zabel proved that all slopes are characterizing for the trifold and the figure 8. So I think these knots are all knots for which all characterizing slopes are known. So these are all knots for which all characterizing slopes are known. And then Xinru Zhang and I prove that for torus knot TRS, so here RS are positive, and the GCD of RS is equal to 1. So for torus knot, we can prove that if P over Q is greater than like 30 R squared minus 1 S squared minus 1 over 67, then P over Q is characterized. And Duncan improved this to 43 R over 4 RS minus RS, and also proved a finiteness theorem for non-characterizing slopes. Which are not integers. So he, on one hand, he got a better bound for positive slopes, characterizing slopes, and he also proved a finiteness theorem for non-characterizing slopes, which are not integers. Okay. Well then, but if you use our main theorem, so corollary of our main theorem is that we can get an even better bound. So P over Q greater than or equal to 4G TR S plus 4, which is just 2 times R minus 1 S minus 1 plus 4. Then P over Q is so this 4G, so this 4G plus 4 comes from a result of Duncan. So this number comes from a result of Duncan. But if you compare our corollary with the previous theorem, so I guess in the previous theorem, the critical number is 4G. So actually, it's probably, if you work harder, then you can probably lower this bound to 4G. So probably lower to 4G for most RS. So you can probably lower this for 4G. So when should I stop?
In the next, well, do you have much more that you wanted to say?
Well, I can say as many as possible if you allow, but I just want to know when should I stop, like
Okay.
9 or 5 minutes to 9.
5:02, I think.
Okay, 5 to 9. Okay. So I have 7 minutes.
Perhaps can I ask a quick question?
Yeah.
So the final remark you made there that it's probably lower for most RS, is that for, I mean, is there a heuristic why certain RS would be exceptional, or, you know, is it something which comes out of the proof that, I don't know, what do you mean by that?
Well, because we do know for some RS, 4G is, or 4G plus 1 is not. So for some RS, you cannot lower to 4G. So you can only hope for most RS, you can lower this. But you certainly you cannot do it for one. So I'll show you an example. So I guess, yeah, so I guess there is a gap between 4G RS and 4G TRS plus 4. I think the most interesting case is S is equal to 2, then let's say R is equal to 2n plus 1. Then in this case, G is equal to, so G is equal to n. So in this case, there are some slopes. So these slopes are the most interesting to us. So that is 4n plus 1, 4n plus 2, 4n plus 3, and 4n plus 4. So this is reducible. So this surgery is reducible. And these two are length spaces. And these two are prism manifolds. But I think the case of length space was already proved by Green. So he already proved that 4n plus 2 are characterizing for these knots. And for prism manifolds, that was proved by me and Xinru Zhang. We proved for these two slopes, they are characterizing. And for length spaces, the case 4n plus 3 was already known by Rasmussen. That 4n plus 3 are characterizing for length spaces. So the only remaining case which was not in the literature was the case 4n plus 1. So if you focus on this special case, then we can show that so 4n plus 1 is characterizing for T2n plus 1, 2, unless n is equal to 2. Unless n is equal to 5. Unless n is equal to 5. So, and actually when n is equal to 5, we know the 21 surgery on T11.2 is actually the same as the 21 surgery on T54, which is just L space and length space So this is 21. Okay, so maybe just in the last 2 minutes, I briefly mention why we can do this. As we said, this fractional thin twist coefficient, so this is basically essentially of phi. This is also known as, so maybe 1 over this is also known as the degeneracy. This is slope. And then there is a theorem of Gabay, which said that if the delta of P over Q and the degeneracy slope is greater than or equal to 3, then this has a genuine lamination. And then there is a theorem of Greatham and Klaus said that Seifert fiber spaces do not have genuine laminations. And also, we want to use another result of Gabay. So if you have a knot in S3 is hyperbolic fibered, then the degeneracy slope should be either n over 0 or n over 1 for some, this n is 2 less than or equal to the absolute value of n less than or equal to 4gk minus 2. So basically, you combine this result. So let me just briefly prove the theorem. So if P over Q greater than 4G, then this implies that delta of P over Q, so by Gabay's theorem, since n is less than or equal to 4gk minus 2, so by Gabay's theorem, it means that delta P over Q and the degeneracy slope is greater than or equal to 3. Then you use Greatham and Klaus. This implies that, I also use Gabay's theorem. Then you know that there is a genuine lamination. Then you use Greatham and Klaus, then you know this is not Seifert. So that's the sketch of the proof. Okay, that's what I want to say. Thank you.
Okay.
I'm sorry. I thought Gabay's result is the distance is greater than or equals to 2.
Yeah, right. So actually, there are 2 parts. So Gabay proved that if the distance greater than or equal to 2, then this implies that the lamination is essential lamination.
Oh.
And if greater than or equal to 3 implies this is a genuine lamination.
Oh, I see. I see.
Yeah,
but
right.
It's not,
so,
okay.
Yeah.
You want the non-trivial complement.
Yeah. Right.
Okay.
Yeah. So yeah, if you essential, so actually in the literature, you can find the part about the essential lamination, but the part about genuine lamination, although it follows from Gabai's argument, but he didn't explicitly state this. But this statement can be found in a paper of Brittenham. Again, he didn't include it in any theorem. He just say from this you can also get the when distance is at least 3 dimensions.
But I guess the 2 still works in general if the degeneracy slope is not like a maximum or anything. If there are some non-trivial complement region in the interior, then you still can get genuine lamination. Is that right?
Yeah, I think for 2, I think you can also. I think you are probably true. But then you need to know more about the lamination itself. So, yeah, well, yeah, but I guess if for my theorem, it doesn't matter. So we know there is a bound. So it doesn't matter to me whether the bound is like 4G or 4G,
okay.
4G minus 1.
So, I mean, maybe this is because I don't know much about laminations, but is there any hope that you can get sort of more control over the Seifert fibered spaces you get out? For example, in terms of numbers of fibers or anything like that?
Number of singular fibers?
Exceptional fibers, sorry.
Yeah, right. I guess I forgot to say this imply that this is not an atoroidal Seifert fiber. Yeah, right. I should say atoroidal. Yeah, atoroidal Seifert fiber spaces do not have genuine lamination. So yeah, so these results are only for atoroidal Seifert fiber.
Okay, so you still can't obstruct more fibers.
Yeah.
Okay. Okay. I guess if there are no more questions, then let's thank you again.
Okay, thank you.
Yeah, thank you.
Oh, you there? Oh, yeah, right. Thank you.
Oh, okay. He's gone. Okay, immediately.
All right.